I'm Pat Dugas. This screencast is about solving systems with linear inequalities using graphical methods. Alright, so in solving linear inequalities, we're going to use the process of graphing each inequality one at a time and shading the appropriate region. Look at the previous screencast on solving linear inequalities if you need help with that. So we do that for each inequality in the system, and in the end, we look for the region that has the overlap of all the solutions for all the inequalities. So the solutions to all the inequalities together will produce one region that they have in common, and that is the solution to the system. So we're going to use that to solve the system of inequalities given by graphing. We're going to graph them. So this inequality system has y greater than or equal to 2x minus 3 and y less than negative x plus 2. So let's start by graphing the first inequality, y is greater than or equal to 2x minus 3. We're going to plot that boundary line, y equals 2x minus 3, and it's going to be a solid line. Okay, and that looks something like this. We've got a y-intercept at negative 3, we have a slope of 2, up 2 over 1, up 2 over 1. That's this solid line. Now we're going to shade the appropriate half plane. We're going to test 0, 0. If we put a 0, 0 into this equation for the boundary line, we get 0 is greater than or equal to negative 3. That is a true statement. Therefore, the top half plane is shaded. And so we have this region in blue as our solution to the first inequality. So let's look now at y less than negative x plus 2 and graph it. So we're going to graph the line y equals negative x plus 2. And it's going to look like, after we shade it, look something like this. It is got a y-intercept of positive 2, that's the b of 2, and then it's got a slope of negative 1, meaning that it's moving down to the right, down 1 over 1 for each unit. And it is dashed because this is a less than situation. When we plot the solution to this inequality, we get everything that's below the dashed line. The solution to the first inequality was everything above the solid line. The solution to this inequality, the second one, is everything that's below the dashed line. What we're looking for is what they have in common, and that is the area that's the darker blue. It's common to both the first inequality and the second. So it's this, it looks like a pentagon, but it actually does go on forever. This triangular area here in dark blue is the solution to our linear system of inequalities. Let's look at another example where our system of inequalities is y greater than or equal to negative 3/4 x plus 1 and y less than or equal to negative 3/4 x minus 2. So we can kind of see that these lines are going to be parallel because their slopes are the same. They both have a slope of negative 3/4. So the two boundary lines are going to be parallel lines. So it'll be interesting to see what happens when we graph this. We'll begin by graphing the boundary line for the first inequality. Y equals negative 3/4 plus 1 has a y-intercept at 1 and a slope of negative 3/4, meaning that it goes down 3 as we go to the right and over 4. So my next point I could plot will be right down here at 4, negative 2 in addition to the intercept, and that would help me create that line. So now we're going to test 0, 0. Well, if I put in a 0, 0 into this first inequality, I get 0 is greater than or equal to 1. That is false. Therefore, 0, 0 is not in the half plane containing the solution to the first inequality. It's above the solid line. So let's graph it and see what that looks like. Medium green area is the half plane that contains the solution to the first inequality. So let's go ahead and tackle the second one. The second one is y equals negative 3/4 x minus 2. It's got a y-intercept of negative 2, 0, negative 2. It has a slope of negative 3/4 as well, so it's parallel to the first line. We go down 3 and over 4, and we come to that point. We can plot a line through that. That's our second boundary line. It is solid as well because we're talking about a less than or equal to. Let's graph y is less than or equal to negative 3/4 x minus 2, and we get this bottom area because if I put 0, 0 into that I get 0 less than or equal to -2, which is a false statement. So again, 0, 0 is not in that half plane either. Everything below the boundary line is part of the solution to the second inequality. So our last step is to see what areas do they have in common. They have none. Therefore, there is no solution to this. This is an inconsistent system of linear inequalities because there is no solution. So let's go ahead and find the vertices of the region formed by the inequalities that you see here. Sometimes finding those vertices is very important. We're going to see that in the next screencast on optimization through linear programming, which is all about finding those vertices, because it turns out a lot of times the maximums and minimum values occur at vertices, the corner points, if you will. So we're going to kind of go a little faster in the graphing portion of this. Let's take the first inequality, 2x minus y greater than or equal to 1. So we're going to plot the line 2x minus y equals -1 as a boundary line. You can see it in green here. The intercepts at -1/2 for x and +1 for y. Each square in this graph is 1/2 unit. It is solid because it is a greater than or equal to. Test 0, 0, we get 0 greater than or equal to -1, which is a true statement. So the inequality here is going to be below the boundary line. Then we're going to plot x plus y less than or equal to 4. Intercepts at +4 for x and +4 for y, also in standard form. It's solid because it's a less than or equal to. When we plot it, we get everything below the blue line. And finally, we have x plus 4y greater than or equal to 4. We'll plot x plus 4y equals 4. X-intercept at 4, y-intercept at negative, a y-intercept at +1. And we get this reddish line here. If we test 0, 0 in that, we get 0 is greater than or equal to 4, which is false. Therefore, it's going to be the area above the red line. Okay, so now we're going to find out what's the region they have in common. Well, it's above the red line, it's below the blue line, and to the right or below the green line, it's this triangular region right here, formed by these 3 points. Now, we can do one of two things here. First of all, graphically, if we've done a really good job graphing, those vertices are easy to find at the intersections of the boundary lines. So the point 0, 1, the point 1, 3, and the point 4, 0 graphically represent our vertices, our corner points. Another way to find the corner points is to find the intersections of the appropriate lines. So for example, to find 1, 3, I'm going to solve the system of the green line and the blue line. 2x minus y equals -1 and x plus y equals 4. Solve that algebraically. I'm going to get 1, 3 as the solution. In a similar way, if I use analytic methods to determine the intersection of the system of the green and the red lines, I'm going to take 2x minus y equals -1 and x plus 4y equals 4, set them equal to each other, go through the process of solving that, and I'm going to get 0, 1. And in a similar way, by setting the blue and the red lines equal to each other, by solving the system of the blue line and the red line, we'll get to point 4, 0. So you can either do that graphically or analytically. This screencast was about solving systems of linear inequalities using graphing of their shaded regions and where they overlap.